Welcome back, and congratulations on getting this far. I sure am glad we didn't lose you in all those loops we covered in the last module. You're doing great and making tons of progress. In earlier videos, we covered the basic elements of Python syntax. We talked about how to define functions, how to make your computer act differently based on conditionals, and how to make it perform operations repeatedly using while and for loops and recursion. Now that we have the basics of syntax out of the way, we can start growing our Python knowledge, which will let us do more and more interesting operations. Remember, one of our main goals in this course is to help you learn to write short Python scripts that automate actions. You've made big steps towards getting there. And in the upcoming videos, we're going to learn a bunch of new, super useful skills to add to your programming toolbox. We'll check out some data types provided by the Python language to help us solve common problems with our scripts. In particular, we'll do a deep dive into strings, lists, and dictionaries. Heads up, while we've used strings in our scripts already, we barely scratched the surface of all the things we can do with them in Python. We also ran into a few lists in some examples, but there's a lot more of them we haven't seen yet. And dictionaries are a whole new data type for us to dig our teeth into. These are all data types, or data structures, that are super flexible. We're going to use them to write all kinds of scripts in Python, so it's a good idea to spend some time getting to know them and learning when to use them and how to make the most out of them. We've got a lot of new and exciting concepts to discover, so let's get right to it. By now, we've used strings in a lot of examples, but we haven't spent time looking at them in detail yet. Before we dive into the nitty-gritty though, let's go over what we've seen so far and add a few more points. First, a quick refresher. A string is a data type in Python that's used to represent a piece of text. It's written between quotes, either double quotes or single quotes, your choice. It doesn't matter which type of quotes you use as long as they match. If we mix up double and single quotes, Python won't be too happy and it'll return a syntax error, telling us it couldn't find the end of the string. A string can be as short as 0 characters, usually called an empty string, or really long. We also learned that we can use strings to build longer strings using the plus sign, an action called concatenating. A less common operation is to multiply the string by a number, which multiplies the content of the string that many times, like this. If we want to know how long a string is, we can use the len function, which we saw in earlier videos. The len function tells us the number of characters contained in the string. We can use strings to represent a lot of different things. They can hold a username, the name of a machine, an email address, the name of a file, and any other text. A lot of the data that we'll interact with will be stored in strings, so it's important to know how to use them. There are tons of things we could do with strings in our scripts. For example, we can check if files are named a certain way by looking at the file name and seeing if they match our criteria. Or we can create a list of emails by checking out the users of our system and concatenating our domain. I recently wrote a script that worked with a bunch of files and took different actions according to the name of each file. So if the file ended in a certain extension, say .txt, then my script would print it. If the file had a certain string in the name, say test, then my script would ignore it and move on to the next thing, and so on. The contents of a text file are also strings. A few months ago, I had to change the default values for a bunch of configuration options from true to false. So I wrote a function that would find the string true in a file and replace it with false. You can probably think of more examples where your code needs to handle strings, but to use strings effectively, we need to know what options are available to us in Python. In the next few videos, we'll cover some of the operations we can perform over strings, including how to access parts of them and modify them. When we first came across the for loop, we called out that we can iterate over a string, character by character. But what if we want to access just a specific character or characters? We might want to do this, for example, if we have a text that's too long to display and we want to show just a portion of it. Or if we want to make an acronym by taking the first letter of each word in a phrase. We can do that through an operation called string indexing. This operation lets us access the character in a given position or index using square brackets and the number of the position we want, like this. This might seem confusing at first, like Python is acting up. We're asking for the first character and it's giving us the second. What gives, Python? Well, what's happening here is that Python starts counting indexes from 0, not 1, just like it does with the range function. So if we want the first character, we need to access the one at index 0. Knowing that indexes start at 0, which one do you think will be the last index in the string? It'll always be one less than the length of the string. In this case, our string has 6 characters, so the last index will be 5. Let's try it out. We see that the character in position 5 is the last character of the string. And if we try to access index 6, we get an index error, telling us that it's out of range. We can only go up to length minus 1. Well, what if you want to print the last character of a string, but you don't know how long it is? You can do that using negative indexes. Let's see that in a different example. In this example, we don't know the length of the string, but it doesn't matter. Using negative indexes lets us access the positions in the string starting from the last. Nice, right? On top of accessing individual characters, we can also access a slice of a string. A slice is the portion of a string that can contain more than one character, also sometimes called a substring. We do that by creating a range using a colon as a separator. Let's see an example of this. The range we use when accessing a slice of a string works just like the one created by the range function. It includes the first number, but goes up to 1 less than the last number. In this case, we start with index 1, the second letter of the string, and go up to index 3, the fourth letter of the string. Another option for the range is to include only one of the 2 indexes. In that case, it's assumed that the other index is either 0 for the first value or the length of the string for the second value. Check this out. Accessing the slice from nothing to 4 takes the first 4 characters of the string, indexes 0 to 3. Accessing the slice from 4 to nothing takes everything from index 4 onward. All of this indexing might seem confusing at first. Don't worry, we all took time to wrap our heads around it. Just like all the challenges we've come across so far, the key is to keep practicing until you master it. And there are a bunch of exercises ahead to help you with that. Now that we know how to select, slice, and access the parts of the string we want, we're going to learn how to modify them. That's coming up next. In the last video, we saw how to access certain characters inside a string. Now, what if we wanted to change them? Imagine you have a string with a character that's wrong and you want to fix it, like this one. Taking into account what you learned about string indexing, you might be tempted to fix it by accessing the corresponding index and changing the character. Let's see what happens if we try that. Oops, these pesky type errors, right? In this case, we're told that strings don't support item assignment. This means that we can't change individual characters because strings in Python are immutable, which is just a fancy word meaning they can't be modified. What we can do is create a new string based on the old one, like this. Nice! We fixed the typo. But does this mean the message variable can never change? Not really. We can assign a new value to the same variable. Let's do that a couple of times to see how it works. What we're doing here is giving the message variable a whole new value. We're not changing the underlying string that was assigned to it before. We're assigning a whole new string with different content. If this seems a bit complex, that's okay. You don't need to worry about this right now. We'll call this out whenever it's relevant for the program we're writing. So we figured out how to create a new message from the old one, but how are we supposed to know which character to change? Let's try something different. In this case, we're using a method to get the index of a certain character. A method is a function associated with a specific class. We'll talk a lot more about classes and methods later. For now, what you need to know is that this is a function that applies to a variable, and we can call it by following the variable with a dot. Let's try this a few more times. So the index method returns the index of the given substring inside the string. The substring that we pass can be as long or as short as we want. What if there's more than one of the substring? Here, we know there are two S characters, but we only get one value. That's because the index method returns just the first position that matches. And what happens if the string doesn't have the substring we're looking for? The index method can't return a number because the substring isn't there, so we get a value error instead. We said that if the substring isn't there, we would get an error. So how can we know if a substring is contained in a string to avoid the error? Let's check this out. We can use the keyword in to check if a substring is contained in a string. We came across the keyword in when using for loops. In that case, it was used for iteration. Here, it's a conditional that can be either true or false. It'll be true if the substring is part of the string, and false if it's not. So here, the dragon's substring isn't part of the string, and sadly, we can't have a dragon as a pet. All right. We just covered a bunch of new things, and you're doing awesome. Let's put all this stuff together to solve a real-world problem. Imagine that your company has recently moved to using a new domain, but a lot of the company email addresses are still using the old one. You want to write a program that replaces this old domain with the new one in any outdated email addresses. The function to replace the domain would look like this. This function is a bit more complex than others, so let's go through it line by line. First, we define the replace domain function, which accepts three parameters: the email address to be checked, the old domain, and the new domain. Having all these values as parameters instead of directly in the code makes our function reusable. We aren't just changing one domain to the other. We have a function that will work with all domains. Pretty sweet! In the first line of the body of the function, we check if the concatenation of the @ sign and the old domain are contained in the email address using the keyword in. We check this to make sure the email has old domain on the portion that comes after the @ sign. If the condition is true, the email address needs to be updated. To do that, we first find out the index where the old domain, including the @ sign, starts. We know that this index will be a valid number because we've already checked that the substring was present. So, using this index, we create the new email. This is a string that contains the first portion of the old email up until the index we had calculated, followed by the @ sign and the new domain. Finally, we return this new email. If the email didn't contain the new domain, then we can just return it, which is what we do in the last line. Wow, that was a really complex function with a lot of new things in it, so don't worry if you're finding it a bit tricky. Rewatch the video and take your time. If there's a specific part that's tripping you up, remember, you can always ask your fellow learners for help in the discussion forum. You may even find that someone has asked and got the answer to the same question already. When you feel ready to move on, meet me over in the next video where we're going to learn a lot more handy string methods. We said earlier that we had a lot of new exciting concepts coming up. Well, I'm not going to string you along anymore. We're going to tie up our lessons on strings with a bunch of fun methods for transforming our string text. I know. My jokes are pretty terrible, so let's get back to the good stuff. So far, we've seen ways you can access portions of strings using the indexing technique, create new strings by slicing and concatenating, find characters in strings using the index method, and even test if one string contains another. On top of all this string processing power, the string class provides a bunch of other methods for working with text. Now we'll show you how to use some of these methods. Remember, the goal is not for you to memorize all of this. Instead, we want to give you an idea of what you can do with strings in Python. Some string methods let you perform transformations or formatting on the string text, like upper and its opposite, lower. These methods are really useful when you're handling user input. Let's say you wanted to check if the user answered yes to a question. How would you know if the user typed it using upper or lowercase? You don't need to. You just transform the answer to the case you want. Like this example. Another useful method when dealing with user input is the strip method. This method will get rid of surrounding spaces in the string. If we ask the user for an answer, we usually don't care about any surrounding spaces, so it's a good idea to use the strip method to get rid of any white space. This means that strip doesn't just remove spaces, it also removes tabs and new line characters, which are all characters we don't usually want in user-provided strings. There are two more versions of this method, lstrip and rstrip, to get rid of the white space characters just to the left or to the right of the string instead of both sides. Other methods give you information about the string itself. The method count returns how many times a given substring appears within a string. The method ends with returns whether the string ends with a certain substring. The method isNumeric returns whether the string's made up of just numbers. Adding to that, if we have a string that is numeric, we can use the int function to convert it to an actual number. In earlier videos, we showed that we can concatenate strings using the plus sign. The join method can also be used for concatenating. To use the join method, we have to call it on the string that'll be used for joining. In this case, we're using a string with a space in it. The method receives a list of strings and returns one string with each of the strings joined by the initial string. Let's check out another example. Finally, we can also split a string into a list of strings. The split method returns a list of all the words in the initial string, and it automatically splits by any white space. It can optionally take a parameter and split the strings by another character, like a comma or a dot. Are you starting to see how these string methods could be useful in your IT job? Okay, so we've just learned a bunch of new methods, but there are tons more that you can use on strings. We've included a list with the ones we talked about and some new ones in the next cheat sheet. You'll also find a link to the full Python documentation there, which gives you all the info on each available method. As we've said before, don't worry about trying to memorize everything. You'll pick these concepts up with practice, and the documentation is always there if you need it. All right, last up in our string of string videos, we're going to check out how to format strings. Up to now, we've been making strings using the plus sign to just concatenate the parts of the string we wanted to create. And we've used the str function to convert numbers into strings so that we can concatenate them too. This works, but it's not ideal, especially when the operations you want to do with the string are on the tricky side. There's a better way to do this, using the format method. Let's see a couple of examples. In this example, we have two variables, name and number. We generate a string that has those variables in it by using the curly brackets placeholder to show where the variables should be written. We then pass the variables as a parameter to the format method. See how it doesn't matter that name is a string and number is an integer? The format method deals with that, so we don't have to. Pretty neat, right? The curly brackets aren't always empty. By using certain expressions inside those brackets, we can take advantage of the full power of the format expression. Heads up, this can get complex fast. If at any point you get confused, don't panic. You only really need to understand the basic usage of the format method we just saw. One of the things we can put inside the curly brackets is the name of the variable we want in that position to make the whole string more readable. This is particularly relevant when the text can get rewritten or translated and the variables might switch places. In our earlier example, we could rewrite the message to make the variables appear in a different order. In that case, we'd need to pass the parameters to format in a slightly different way. Because we're using placeholders with variable names, the order in which the variables are passed to the format function doesn't matter. But for this to work, we need to set the names we're going to use and assign a value to them inside the parameters to format. And that's just the tip of the iceberg of what we can do with the format method. Want to dive a little deeper? Great, let's keep on going. We're going to check out a different example. Let's say you want to output the price of an item with and without tax. Depending on what the tax rate is, the number might be a long number with a bunch of decimals. So if something costs $7.5 without tax and the tax rate is 9%, the price with tax would be $8.175. First off, ouch. And also, since there's no such thing as half a penny anymore, that number doesn't make sense. So to fix this, we can make the format function print only 2 decimals, like this. In this case, between the curly brackets, we're writing a formatting expression. There are a bunch of different expressions we can write. These expressions are needed when we want to tell Python to format our values in a way that's different from the default. The expression starts with a colon to separate it from the field name that we saw before. After the colon, we write .to_f. This means we're going to format a float number and that there should be 2 digits after the decimal dot. So no matter what the price is, our function always prints 2 decimals. Remember when we did the table to convert from Fahrenheit to Celsius temperatures? Our table looked kind of ugly because it was full of float numbers that had way too many decimal digits. Using the format function, we can make it look a lot nicer. In these 2 expressions, we're using the greater than operator to align text to the right so that the output is neatly aligned. In the first expression, we're saying we want the numbers to be aligned to the right for a total of 3 spaces. In the second expression, we're saying we want the number to always have exactly 2 decimal places, and we want to align it to the right at 6 spaces. We can use string formatting like this to make the output of our program look nice, and also to generate useful logging and debugging messages. Over the course of my sysadmin career, I've grown used to formatting strings to create more informative error messages. They help me understand what's going on with a script that's failing. There's a ton more formatting options you can use when you need them, but don't worry about learning them all at once. We'll explain any others as they come along, and we'll put everything in a cheat sheet that you can refer to whenever you need a formatting expression. Let's take a look at that now, and then we'll have a quiz to help you get more familiar with all this new knowledge. As you know by now, Python comes with a lot of ready-to-use data types. We've seen integers, floats, booleans, and strings in detail. But those data types can only take you so far. Eventually, in your scripts, you'll want to develop code that manipulates collections of items, like a list of strings representing all the file names in a directory, or a list of integers representing the size of network packets. This is where the list data type comes in handy. You can think of lists as long boxes, with the space inside the box divided up into different slots. Each slot can contain a different value. Like we mentioned earlier when we first came across the list, In Python, we use square brackets to indicate where the list starts and ends. Let's check out an example. Here, we've created a new variable called x and set its contents to be a list of strings. We can check the type of x using the type function we saw a little while ago. Nice! Python tells us this is a list. In the same way we've done with other variables, we can show the contents of the whole list using the print function. The length of the list is how many elements it has. To get that value, we'll use the same len function we used for strings. That's right, our list has 4 elements. When calling len for the list, it doesn't matter how long each string is on its own. What matters is how many elements the list has. To check if a list contains a certain element, you can use the keyword in, like in these examples. Again, like when we used this with strings, the result of this check is a Boolean, which we can use as a condition for branching or looping. We can also use indexing to access individual elements depending on their position in the list. To do that, we use the square brackets and the index we want to access, exactly like we did with strings. Remember that the first element is given the index 0. This means the last index of the list will be the length of the list minus 1. What happens if we try to access an element after the end of the list? Ugh, you might have seen this coming. We get an index error. We can't go over the end of the list. Remember that because list indexes start at 0, accessing the item at index 4 means we're trying to access the 5th element in the list. There are only 4 elements, so we're out of range if we try to access the index number 4. Does this seem a bit confusing? If it does, this visualization might help you out. As you can see, index 4 doesn't point at anything since there's no slot 4 in our list. As with strings, we can also use indexes to create a slice of the list. For this, we use ranges of 2 numbers separated by a colon. Again, the second element isn't included in the slice, so the range goes to the second index minus 1. Here, we start at index 1 and go up to 1 less than 3, which is 2. We can also leave out one of the range indexes empty. The first value defaults to 0 and the second value to the length of the list. Make sense? If all this sounds really familiar to what we said about strings, then this course is working as intended. That's because strings and lists are very similar data types. In Python, strings and lists are both examples of sequences. There are other sequences too, and they all share a bunch of operations, like iterating over them using for loops, indexing, using the len function to know the length of the sequence, using plus to concatenate 2 sequences, and using in to verify if the sequence contains an element. So this is great news. While understanding indexing is hard, once you know it for one data type, you've pretty much mastered it for every data type. So you actually know way more than you thought. Wow, now we're really cooking. Next up, we're going to look at some more list operations, this time actually specific to lists. One of the ways that lists and strings are different is that lists are mutable, which is another fancy word to say that they can change. This means we can add, remove, or modify elements in a list. Let's go back to our example of thinking of a list as a long box. Changing the list means we keep the same box and we add, remove, or change the elements inside that box. We'll now go through the methods that let us modify the list one by one. If all these details seem a little overwhelming, that's okay. As usual, there will be a cheat sheet at the end and you'll have lots of chances to practice each of these methods as we go along. You don't need to learn all those by heart, and of course you can always review anything that isn't clear. So don't worry, we've got your back. We'll start with the simplest change, adding an element to a list using the append method. Let's check this out in the tastiest example yet. The append method adds a new element at the end of the list. It doesn't matter how long the list is, the element always gets added to the end. You could start with an empty list and add all of its items using append. If you want to insert an element in a different position instead of at the end, you can use the insert method. The insert method takes an index as the first parameter and an element as the second parameter. It adds the element at that index in the list. To add it as the first element, we use index 0, and we can use any other number. What happens if we use a number larger than the length of the list? Woohoo! No errors! You can say that it even worked just peachy. If we use an index higher than the current length, the element just gets added to the end. You can pass any number to insert, but usually you either add at the beginning using insert at the 0 index or at the end using append. We can also remove elements from the list. We can do it using the value of the element we want to remove. Can you guess what method we would use? You got it! Use the remove method. The remove method removes from the list the first occurrence of the element we passed to it. What happens if the element is not in the list? Oof, that went pear-shaped. We got a value error telling us the element isn't in the list. Another way we can remove elements is by using the pop method, which receives an index. The pop method returns the element that was removed at the index that was passed. And the last way to modify the contents of a list is to change an item by assigning something else to that position, like this. Wow, the contents of our fruits variable have changed a lot since we started this video, but it's always the same variable, the same box. We've just modified what's inside. Modifying the contents of lists will come up in tons of scripts as we operate with them. If the list contains hosts on a network, you could add or remove hosts as they come online or offline. If the list contains users authorized to run a certain process, you could add or remove users when permissions are granted or removed, and so on. You've now seen a number of methods that let us modify the contents of a list, adding, removing, and changing the elements that are stored inside the list. Whenever you need to write a program that'll handle a variable amount of elements, you'll use a list. What if you need a sequence of a fixed amount of elements? That's coming up in our next video. As we called out before, there are a number of data types in Python that are all sequences. Strings are sequences of characters and are immutable. Lists are sequences of elements of any type and are mutable. A third data type that's a sequence and also closely related to lists is the tuple. Tuples are sequences of elements of any type that are immutable. We write tuples in parentheses instead of square brackets. You might be wondering, why do we even need another sequence type? Weren't lists great? Yes, lists are great. They can hold any number of elements, and we can add, remove, and modify their contents as much as we want. But there are cases when we want to make sure an element in a certain position or index refers to one specific thing and won't change. In these situations, lists won't help us. Thanks for nothing, lists. In our example, we have a tuple that represents someone's full name. The first element of the tuple is the first name, the second element is the middle initial, and the third element is the last name. If we add another element somewhere in there, what would that element represent? It would just be confusing, and our code wouldn't know what to do with it. and that's why modifying isn't allowed. In other words, when using tuples, the position of the elements inside the tuple have meaning. Tuples are used for lots of different things in Python. One common example is the return value of functions. When a function returns more than one value, it's actually returning a tuple. Remember the function to convert seconds to hours, minutes, and seconds that we saw a while back? Here it is to remind you. This function returns 3 values. In other words, it returns a tuple of 3 elements. Let's give it a try. We see the result as a tuple. What if we print it? We see that it has the 3 elements we expect it to have. And remember, since this is a tuple, the order matters. The first element represents the hours, the second one represents the minutes, and the third represents the seconds. One interesting thing we can do with tuples is unpack them. This means that we can turn a tuple of 3 elements into 3 separate variables. And because the order won't change, we know what those variables represent. Like this. So, now we've split the tuple into 3 separate values. We've seen before that we can also do this directly when calling the function without the intermediate result variable. In Python, it's really common to use tuples to represent data that has more than one value and that needs to be kept together. For example, you could use a tuple to have a file name and its size, or you could store the name and email address of a person, or a date and time and the general health of a system at any point in time. Can you see how these different data types could help you automate some of your IT work? Pretty cool, right? Knowing when to use tuples and when to use lists can seem a little fuzzy at first, but don't worry, it'll get clearer as we tackle more examples. When we looked at for loops, we said they iterate over a sequence of elements. One of the examples we checked out was iterating over a list. Let's take a little trip to the zoo to see this in action. Okay, so we will make a list of animals. So, animals equals, and since we're making a list, we'll start with a bracket. And we'll add lion, zebra, dolphin, and monkey. And end the list with another bracket. Chars equals 0. And we'll start a loop. For animal in animals, 2 spaces, chars, plus equals length of animals. Print total characters average length dot format chars length animals. In this code, we're iterating over a list of strings. For each of the strings, we get its length and add it to the total amount of characters. At the end, we print the total and the average, which we get by dividing the total by the length of the list. You can see we're using the len function twice, once to get the length of the string, and then again to get the amount of elements in the list. What if you wanted to know the index of an element while going through the list? You could use the range function and then use indexing to access the elements at the index that range returned. You could use a range function and then use indexing to access the elements at the index that range just returned. Or you could just use the enumerate function. Winners equals, we'll make a list, Ashley,
Dylan, and Reese. And close the list. For index person in enumerate winners, print curly brackets dash curly brackets dot format index plus 1 person.
The enumerate function returns a tuple for each element in the list. The first value in the tuple is the index of the element in the sequence. The second value in the tuple is the element in the sequence. You're the real winner with the enumerate function. It does all the work for you. Pretty useful, right? Let's use all of this now to solve a slightly more interesting problem. Say you have a list of tuples containing 2 strings each. The first string is an email address, and the second is the full name of the person with that email address. You want to write a function that creates a new list containing 1 string per person, including their name and the email address between angled brackets, the format usually used in emails, like this. So, what do we need to do? We'll start by defining a function that receives a list of people.
Def full emails takes the argument people.
Remember, people is a list of tuples where the first element is the email address and the second one is the full name. So in our function, we'll first create the variable that we'll use as a return value, which will be a list, and we'll call it result.
Result equals empty list.
We'll then iterate over the list of people. We know this list contains tuples of 2 strings each, so we'll unpack the values directly when iterating in variables that we'll call email and name.
For email and name in people,
now our result variable is a list, and it should contain strings, so we'll append the resulting string to the results list.
Result.append.
The string that we'll append will be formatted in the way we want. To do that, we'll use the format method with the 2 variables of our iteration.
So curly brackets, dot format, name, and email.
Once we're done with the iteration, we'll return the list, which should now contain all the necessary emails.
Return result.
Will this work? What do you think? Let's try it out.
Print full emails. Alex@example.com. Alex Diego. Shay@example.com is the email, and we'll call Shay Brand as the name.
Yes, this worked as expected. Before we move on, a quick word of caution about some common errors when dealing with lists in Python. Because we use the range function so much with for loops, you might be tempted to use it for iterating over indexes of a list, and then to access the elements through indexing. You could be particularly inclined to do this if you're used to other programming languages before. Because in some languages, the only way to access an element of a list is by using indexes. Real talk. This works, but looks ugly. It's more idiomatic in Python to iterate through the elements of the list directly, or using enumerate when you need the indexes, like we've done so far. There are some specific cases that do require us to iterate over the indexes. For example, when we're trying to modify the elements of the list we're iterating. By the way, if you're iterating through a list and you want to modify it at the same time, you need to be very careful. If you remove elements from the list while iterating, you're likely to end up with an unexpected result. In this case, it might be better to use a copy of the list instead. We've now seen a bunch of different things we can do with lists, and hopefully you're starting to see how they can be a very powerful tool in your IT specialist toolkit. Next up, we're going to learn a powerful technique for creating lists. We're almost done with our deep dive into Python lists. But before we continue to our next data structure, let's talk about creating lists in a shorter way. Say we wanted to create a list with multiples of 7, from 7 to 70. We could do it like this.
So we create a list called multiples. Then, for x in range 1 to 11, multiples dot append x times 7. Print multiples.
This works fine and is a good way of solving it, but because creating lists based on sequences is such a common task, Python provides a technique called list comprehension that lets us do it in just one line. This is how we would do the same with list comprehension.
Multiples equals, we'll start the list, x times 7 for x in range 1 to 11, and close the list. Print multiples. It should be the same.
List comprehensions let us create new lists based on sequences or ranges. So we can use this technique whenever we want to create a list based on a range, like in this example, or based on the contents of a list, a tuple, a string, or any other Python sequence. The syntax tries to copy how you would express these concepts with natural language, although it can still be confusing sometimes. Let's check out a different example. Say we have a list of strings with the names of programming languages, like this one, and we want to generate a list of the lengths of the strings. We could iterate over the list and add them using append like we did before, or we could use a list comprehension, like this.
Lengths equals len language for language in languages. Print lengths.
List comprehensions also let us use a conditional clause. Say we wanted all the numbers that are divisible by 3 between 0 and 100. We could create a list like this.
Z equals, open list, x for x in range 0 to 101 if x modulo 3 equals 0. Print z.
In this case, we just want the element x to be a part of the list, but we only want the numbers where the remainder of the division by 3 is 0. So we add the conditional clause after the range. Using list comprehensions when programming in Python is totally optional. Sometimes it can make the code look nicer and more readable. At other times, it can have the opposite effect, especially if we try to pack too much information together. In general, it's a good idea to know that list comprehensions exist, especially when you're trying to understand someone else's code. All right, we've now seen a bunch of different methods we can use to operate with lists and tuples, and Python provides even more of them that we didn't get to talk about. In our next reading, you'll find a list of the most common operations and links to the official documentation in case you want to learn more. After the reading, you can practice your new skills in the next quiz. Welcome back! The first time we talked about list comprehensions, we showed you how to create a list using a for loop. Then we showed you how to create that same list using a list comprehension. If you're anything like me, you're probably wondering why there are two ways to do the same thing. So how do you know which one to use? In this video, we're going to talk about when to use a for loop and when to use a list comprehension. But first, a quick review. We said a for loop iterates or repeats over a sequence of values like numbers, letters, and so on. A list comprehension lets us create new lists based on sequences or ranges. It's basically a shorthand way to build a new list based on the contents of an existing list. The list comprehension has the for loop, the compilation, and builds the list all in a single line of code. List comprehensions and for loops both do the same thing. So when should you use which one? The short answer is, it's your call. Both methods are essentially interchangeable, so there are no standards or best practices. Deciding when to use a list comprehension instead of a for loop or vice versa is totally up to you. That said, there are considerations that many programmers make when deciding whether to use a list comprehension or a for loop. Programmers tend to use a list comprehension when it's fairly simple code, such as filtering a list to pull out items that match or capitalizing words in a list. If it can fit on a single line, I'd probably make it a list comprehension, which you can see in this example. For more complex code, it's usually a good idea to use a for loop. A for loop spells out the process better, which will make it easier for you and other programmers to read and maintain the code you write. For example, let's say you're working for a company that maintains a list of invoices. You need to calculate the sales tax and balance due for all the items on the list. You want to start with updating the status of past due invoices. You could accomplish this with a list comprehension, but it would be complicated and likely confusing to read and understand. Let's go over an example of what the list comprehension would look like for updating the status of past due invoices. In this code, we create a list called past due that contains all of the invoices in the invoices list that are more than 30 days old and have not yet been paid. I is used in the list comprehension to iterate over the invoices list. Then, for j in past due iterates over the past due list and sets the status of each invoice to past due. J is used in the for loop to iterate over the past due list. In this case, a for loop would be preferable because it clearly lays out all the steps the code is going through, so other programmers can read and understand it quickly. Here's an example of what that looks like. This for loop iterates over the invoices list and sets the attribute of each invoice to past due if the invoice is more than 30 days old and has not been paid yet. This code will have the same result as the list comprehension we just went over, but it's more straightforward. This makes it easier to code and understand. So let's loop back to the question we asked earlier. When should you use a for loop, and when should you use a list comprehension? Here are some questions to ask yourself to guide your decision. Which one will make my code both clear and concise? And which one will make my code easier for other people to read and understand? It's important to keep in mind that most developers like their code short, sweet, and to the point. Finally, remember that whatever code writing strategy you choose, use meaningful names for all your variables, data sets, and lists. Always assume others will see your code. And now that you're armed with the information to make the best decisions, you can continue building your knowledge and skills as you dive deeper into Python. How are you feeling so far? Lists and strings are pretty cool, right? These tools let us do a ton of neat stuff in our code, so they can be super fun to experiment with. We're now going to learn about another data type, dictionaries. Like lists, dictionaries are used to organize elements into collections. Unlike lists, you don't access elements inside dictionaries using their position. Instead, the data inside dictionaries take the form of pairs of keys and values. To get a dictionary value, we use its corresponding key. Another way these two vary is while in a list the index must be a number, in a dictionary you can use a bunch of different data types as keys, like strings, integers, floats, tuples, and more. The name dictionaries comes from how they work in a similar way to human language dictionaries. In an English language dictionary, the word comes with a definition. In the language of a Python dictionary, the word would be the key and the definition would be the value. Make sense? Let's check out an example. You can create an empty dictionary in a similar way to creating an empty list, except instead of square brackets, dictionaries use curly brackets to define their content. Once again, we can use the type function to check that the variable we've just created is a dictionary.
X equals, open brackets, type X.
Creating initialized dictionaries isn't too different from the syntax we used in earlier videos to create initialized lists or tuples. But instead of a series of slots with values in them, we have a series of keys that point at values. Okay, let's check out an example dictionary.
We'll call it file counts equals, and then open bracket, JPEG 10, text 14, CSV 2, and PY 23. Print file counts.
In this file counts dictionary, we've stored keys that are strings, like JPEG, that point at integer values like 10. When creating the dictionary, we use colons in between the key and the value and separate each pair by commas. In a dictionary, it's perfectly fine to mix and match the data types of keys and values like this, and can be very useful. In this example, we're using a dictionary to store the number of files corresponding to each extension. It makes sense to encode the file extension formatting in a string, while it's natural to represent a count as an integer number. Let's say you want to find out how many text files there are in the dictionary. To do this, you would use the key txt to access its associated value. The syntax to do this may look familiar, since we use something similar in our examples of indexing strings, lists, and tuples.
File counts, open bracket, txt.
You can also use the in keyword to check if a key is contained in a dictionary. Let's try a couple of keys.
JPEG in file counts, true. HTML in file counts, false.
Dictionaries are mutable. You might remember what mutable means from an earlier video. That's right, it means we can add, remove, and replace entries. To add an entry in a dictionary, just use the square brackets to create the key and assign a new value to it. Let's add a file count of 8 for a new CFG file extension in our dictionary.
File counts, open bracket, add CFG, close bracket, equals 8, and then print file counts.
Oh, this brings up an interesting point about dictionaries. What do you think will happen if we try to add a key that already exists in the dictionary?
File counts, open bracket, CSV, close bracket, equals 17. Print file counts.
When you use a key that already exists to set a value, the value that was already paired with that key is replaced. As you can see in this example, the value associated with the CSV key used to be 2, but it's now 17. The keys inside of a dictionary are unique. If we try to store two different values for the same key, we'll just replace one with the other. Last off, we can delete elements from a dictionary with the del keyword by passing the dictionary and the key to the element as if we were trying to access it.
Del file counts, open bracket, CFG, close bracket, and print file counts.
What do you think? Dictionaries seem pretty useful, right? We've now seen how to create a dictionary and how to add, modify, and delete elements stored in the dictionary. Up next, we'll discover some interesting things we can do with them. It probably won't come as a surprise that, just like with strings, lists, and tuples, you can use for loops to iterate through the contents of a dictionary. Let's see how this looks in action.
So file counts equals, open bracket, JPEG 10, comma, TXT 14, comma, CSV 2, comma, PY 23, and then close bracket. And then for extension in file counts, 2 spaces, print extension.
So, if you use a dictionary in a for loop, the iteration variable will go through the keys in the dictionary. If you want to access the associated values, you can either use the keys as indexes of the dictionary, or you can use the items method, which returns a tuple for each element in the dictionary. The tuple's first element is the key, its second element is the value. Let's try that with our example dictionary.
For extension amount in file counts dot items, print there are, and then brackets, files with the dot brackets extension dot format amount extension.
Sometimes you might just be interested in the keys of a dictionary. Other times you might just want the values. You can access both with their corresponding dictionary methods, like this.
File counts dot keys, file counts dot values.
These methods return special data types related to the dictionary, but you don't need to worry about what they are exactly. You just need to iterate them as you would with any sequence.
For value in file counts dot values, print value.
So we can use items to get key value pairs, keys to get the keys, and values to get just the values. Not too hard, right? Because we know that each key can be present only once, dictionaries are a great tool for counting elements and analyzing frequency. Let's check out a simple example of counting how many times each letter appears in a piece of text. In this code, we're first initializing an empty dictionary, then going through each letter in the given string. For each letter, we check if it's not already in the dictionary, and in that case, we initialize an entry in the dictionary with a value of 0. Finally, we increment the count for that letter in the dictionary. To sum up, we've created a dictionary where the keys are each of the letters present in the string and the values are how many times each letter is present. Let's try out a few example strings.
Count letters, let's say A. Count letters, tenant. Count letters, and this time we'll say a long string with a lot of letters.
Here you can see how the dictionary can have any number of entries, and the pairs of key values always count how many of each letter there are in the string. Also, do you see how our simple code doesn't distinguish between actual letters and special characters like a space? To only count the letters, we'd need to specify which characters we're taking into account. This technique might seem simple at first, but it can be really useful in a lot of cases. Let's say, for example, that you're analyzing logs in your server and you want to count how many times each type of error appears in the log file. You could easily do this with a dictionary by using the type of error as the key and then incrementing the associated value each time you come across that error type. Are you starting to see how dictionaries can be a really useful tool when writing scripts? Coming up, we're going to learn how to tell when to use dictionaries and when to use lists. Dictionaries and lists are both really useful, and each have strengths in different situations. So when is it best to use a list, and when's a dictionary the way to go? Think about the kind of information you can represent in each data structure. If you've got a list of information you'd like to collect and use in your script, then a list is probably the right approach. For example, if you want to store a series of IP addresses to ping, you could put them all into a list and iterate over them. Or, if you had a list of host names and their corresponding IP addresses, you might want to pair them as key values in a dictionary. Because of the way dictionaries work, it's super easy and fast to search for an element in them. Let's say you have a dictionary that has usernames as keys and the groups they belong to as values. It doesn't matter if you have 10 users or 10,000 users. accessing the entry for a given user will take the same time. Amazing! But this isn't true for lists. If you've got a list of 10 elements and you need to check if one element is in the list, it'll be a very fast check. But if your list has 10,000 elements, it'll take significantly longer to check if the element you're looking for is there. So, in general, you want to use dictionaries when you plan on searching for a specific element. Another interesting difference is the types of values that we can store in lists and dictionaries. In lists, you can store any data type. In dictionaries, we can store any data type for the values, but the keys are restricted to specific types. The reasoning behind which types are allowed can get complex, and we don't want to bog you down with unnecessary details. So as a rule of thumb, you can use any immutable data type, numbers, booleans, strings, and tuples as dictionary keys. On the flip side, like we said, the values associated with keys can be any type, including lists or even other dictionaries. You can use them to represent more complex data structures, like directory trees in a file system. There's a ton of different key value pairs that we need to work with in system administration, so I use dictionaries all the time. They're especially useful with large data sets when I need to write a script that gets specific keys out of it to manipulate or modify the associated value. But it doesn't always need to be that serious. One time, just for fun, I wanted to be able to look up which Disney villain is associated with each protagonist. So I created a dictionary that stores a key like Snow White with the value Evil Queen. Pretty good, right? Mirror, mirror on my screen, who's the best coder you've ever seen? There are even more data types available that we haven't checked out yet. One of these data types is a set, which is a bit like a cross between a list and a dictionary. A set is used when you want to store a bunch of elements and be certain that they're only present once. Elements of a set must also be immutable. You can think of this as the keys of a dictionary with no associated values. Or you could see it as a list where what matters isn't the order of the elements, but whether an element is in the list or not. Wow, we've covered a lot and we've still only scratched the surface of what dictionaries can do in your scripts. As you progress in your IT career, you'll come across a lot of situations where a dictionary is the easiest way to organize your data. If you're interested, you can learn more about dictionaries in the official documentation. You'll find links to this in the next reading. Let's take a second to review what you've accomplished so far. We've now gone over all the basic syntax of Python and then checked out the most common data structures, strings, lists, and dictionaries. These let our scripts do a bunch of cool things like processing text, iterating through elements to do an operation on each, finding out the frequency of an element, and a whole lot more. In the next videos, we're going to focus on a bunch of new concepts. We're going to dive into object-oriented programming, which is a way of thinking about and implementing our code. We'll discuss how to create our own objects and how to use many of Python's interesting capabilities. We're going to learn a lot of new terminology too. Okay. Ready for your orientation on object-oriented programming? There's a lot to cover, so let's jump right in. So, how are you doing so far? Is everything making sense? Are all those Apple examples making you hungry? Feel free to pause and grab a snack if that's what you need. We called out earlier that we use methods to get objects to do stuff. We've seen several methods in our example so far, like lower for strings, append for lists, or values for dictionaries. The key to understanding methods is this. Methods are functions that operate on the attributes of a specific instance of a class. When we call the append method on a list, we're adding an element to the end of that specific list and not to any other lists. When we call the lower method on a string, we're making the contents of that specific string lowercase. How exactly does this happen? Let's take a closer look by defining our own methods. First, we need to define a class and create an instance of it, like we've done before. Nice! We've created a piglet class. While our new piglet might be cute, it can't do a whole lot right now. What if we wanted to give it a voice? For objects to perform actions, they need methods. And, as we called out before, a method is a function that operates on a single instance of an object. Let's add a method to our class. You can see here that we start defining a method with the def keyword, just like we would for a function. And see how the line with the def keyword is indented to the right, inside the piglet class? That's how we define a function as a method of the class. This function is receiving a parameter called self. This parameter represents the instance that the method is being executed on. Okay, let's try this out and see what happens.
Hamlet equals piglet, hamlet.speak.
And the piglet goes oink oink. It sure does. But this makes the piglet say the same thing for all instances of the class. Boring. Let's make the method do something different depending on the attribute of the instance. This time, we've started the body of the class by defining an attribute called name with a default value of piglet. We can change that value later, but it's a good idea to set it now to make sure our variable is initialized. If you look closely at how we wrote the new speak method, you'll see that it's using the value of self.name to know what name to print. This means that it's accessing the attribute name from the current instance of piglet. Let's try this out.
So we'll set hamlet equals piglet. Then we can say hamlet.name, and we'll set the name to a string, hamlet. And then we can call .speak on hamlet.
Meet Hamlet, our Python pig. What, you didn't know pigs could talk? Well, they can in Python. In this example, the speak method printed the name Hamlet, which was the name attribute that we set. What if we create a new instance of the same class, but with a different name? It should generate a different output. Okay, let's try this out. I think Hamlet needs a friend. We've now created two instances of the piglet class, each of them with their own name. When calling the speak method, each of them prints their name and not the other. Variables that have different values for different instances of the same class are called instance variables, just like the name variable in this example. Since methods are just functions that belong to a specific class, they can work as any other function, so they can receive more parameters and return values if needed. Let's check out what a method returning a value looks like. In this case, we've created a method that converts the age of our piglet to pig years. So the value that the method returns should change when we change the years attribute of our instance. Let's create an instance and check how this method works. Piggy is 2 years old in human years. How old is he in pig years? So, as the value of the years attribute changes, the return value of the pig years method changes too. Coming up, we're going to learn about a few special types of methods, including one in particular called constructor. In this module, we've covered the basic structures we can use to make the most of our Python scripts: strings, lists, and dictionaries. And we've also called out a couple of associated data types like tuples and sets. Knowing your way around these structures lets you solve interesting problems with your programs. As we keep saying, the key to mastering them and knowing when to use one or the other is practice. The more you write scripts that use these concepts, the easier it'll become to pick the right one when you need it. So, how are you feeling? We just learned a lot of new concepts and it's totally normal to feel a little overwhelmed. If you're feeling confident, that's awesome. And if you're starting to think, this is too hard for me, I'll never get it, that's also completely normal. We all felt like that at some point when learning how to code. First off, you will get this. Second, if you're feeling a little iffy on any of the content we've covered so far, now is the time to rewatch the videos. Believe me, you'll be amazed by how much you've learned so far, and a second review is usually all you need to understand what might seem a little tricky right now. Jobs in IT require problem solving and perseverance. You wouldn't be here right now if you didn't have the grit to learn how to script. So stick with it. I promise you that it'll only get easier and easier. To wrap up, we've got a graded assessment to help you put all your new knowledge to the test. Take it once you feel ready to. Take your time. And remember, you've got this.